Welcome to week 5, lecture 3. We're going to talk about motion of complex objects. This is covering 7-1, 7-2, and 7-3. We're going to go over motion of complex objects, two-particle systems, and many-particle systems. So let's start out with a complex object that is two masses at either end of a massless rod or a baton. This diagram models the motion of a baton being thrown between two people. We can see from this that the motion, appears pretty complicated, but we can break the motion down into three parts. The motion of each mass and motion of the center of mass of the whole system. We can think of the center of mass as the point along the rod where the baton could be balanced. So, for example, with like a pencil, which is not fully visible to you, if you move your fingers and find the point where it balances, that's the center of mass. In this situation, since the masses are uneven, one end is heavier than the other, the center of mass will be closer to that heavier end. So here we have this image that traces the motion of the three parts of the baton. The smaller mass end, the bigger mass end, and the center of mass. And you can see here, so the smaller mass end is kind of this one, it seems like. And the bigger mass end is this one. And then the center of mass is this other one. And within these wavy lines that are coming from the two particles at the end, we have a familiar parabola shape. And that's the motion of the center of mass. And that's something we're familiar with, that parabola. So let's think about this situation with some vectors. We have our baton, here it is, mass 2, mass 1, center of mass. In this XY coordinate axis, the positions of the masses are given by position vectors R1 and R2. So R1 is the position vector for mass 1, R2 is the position vector for mass 2. And then we have RCM giving us the position vector of the center of mass. And we can find the position of the center of mass by taking mass 1 times the position vector 1 plus mass 2 times position vector 2 divided by both masses added together. And you can also do the same thing for the X and Y position of the center of mass. So for example, this is an XY coordinate axis. If we wanted the X and Y coordinates, we could do it this way. We could say, okay, this is the X position of mass 1, this is the Y position of it, and move from there. So now let's look at a time later when the baton has changed position. Now we have the RCM prime, which represents the new position of the center of mass of the object. So we can find the velocity of the center of mass in this motion by taking the time derivative of our position equation. And this gives us the same relationship with velocity that we had with position. So velocity of the center of mass is mass 1 times velocity 1 plus mass 2 times velocity 2 divided by the sum of the masses. We can do this same thing to find the acceleration. So take the time derivative of the velocity here. And we get the same relationship again. Mass 1 times acceleration 1 plus mass 2 times acceleration 2 divided by the sum of the masses. But mass times acceleration from Newton's second law is force. So we can actually rearrange these equations to relate the net force, or sorry, this equation, to relate the net force on the center of mass and the net force on each mass. So if we multiply both sides by the masses added together, we end up with the sum of forces acting on the center of mass, which is equal to the sum of forces acting on mass 1 and the sum of forces acting on mass 2. So we have a sum of forces equation. We're working a little backwards, but why don't we look at a free body diagram for the situation? So we have a free body diagram of each mass and the rod. So mass 1 experiences vertical forces of its weight and normal force, but then the only horizontal force it experiences is this force from the rod. And then mass 2 is the heavier one, so its weight and normal force factors are bigger, but the only horizontal force is again this force from the rod. And then the rod itself, it's just experiencing the two forces from the masses, and those forces are equal and opposite of each other. So sorry, skipped a step. So that tells us that this equation must be 0 since the sum of the forces on 1 are equal and opposite to the sum of the forces on 2. So this side of the equation will be 0. So, and the forces on the masses are internal to the system in this situation, because again, it's just like our system is the two masses in the rod, and the only forces are coming from those. So the center of mass of the system experiences no acceleration in this situation. But if instead we had a situation where there is a net force, external force, sorry, that is acting on the particles, we can start from the same relationship here. The sum of forces on the center of mass is equal to the sum of forces on 1 plus the sum of forces on 2. So this time the sum of forces equations are two forces acting. So there we go. So we have this force we had before from the rod, and then we also have this external force acting on each of the masses. So we know that if we put these equations in here, we know that these forces from the rod are equal and opposite. So those will still cancel, but that doesn't give us 0. So those are equal and opposite. But then we end up with, instead of the sum of forces on the center of mass being 0, we end up with the sum of forces being the external forces acting on each mass, which is mass 1 times acceleration 1 plus mass 2 times acceleration 2. Yeah, and then referring to this relationship for the acceleration of the center of mass again, we find that the sum of external forces acting on the system, that's what this is here, is the sum of the external forces acting, is equal to the sum of the masses times the acceleration of the center of mass of the system. So the sum of the net external forces acting on a system of particles is equal to the total mass times the acceleration of the center of mass of the system. So when there are no net external forces, the center of mass of the system is not accelerating. But when there are external forces, the acceleration can be described by this relationship. Excuse me, we see the same relationship for what we call a mini particle system, or just a system of a bunch of particles. We start with the position here given by 1 divided by the capital M, which is just the sum of all of the masses. Like I said, many particles, so a bunch of different masses. So anyway, the position is given by 1 divided by the total masses in the system, times the sum of the mass of each object times its position. And then we get the same relationship for both velocity and acceleration. And this originates in the same way as for the two-particle system, excuse me, where we just could find these by taking the derivative with respect to time of the previous. So to get the velocity, derivative with respect to time of this. To get acceleration, derivative with respect to time of this. And in turn, we can say the net external force acting on the system is equal to the total mass of the system, because again, that's what capital M is, times the acceleration of the center of mass of the system. So we can treat a many particle system experiencing a net external force like a single particle with all of the mass concentrated at the center of mass. And otherwise, if there's no net external force acting on the system of particles, then the center of the mass of the system does not experience acceleration. That doesn't mean that individual particles don't experience acceleration, but the center of mass itself does not. So that's all I have for this one. I thought wanted to give you some time with the concepts. And we'll continue working with this next week. But yeah, have a great day.